Hi, my name is Juntai, and today I'm going to present the paper using BibTeX to automatically generate label data for citation field extraction. This is joint work with Zhiyang, Nicholas Monath, Boris, Veytsman, and Anzaroot and McCallum. Citation are strings that usually appear in the reference section of a paper and contain information such as title, years, and author names. Given a citation string, the goal is to extract segment fields and tag them with the corresponding labels. Similar to name entity recognition, the citation field extraction is also formulated as a sequence labeling task. The unique feature of this task is its complex constraint between labels. For example, author segments have to be consecutive, and some labels can only appear one per citation, such as years and titles. These constraints vary across domains and disciplines. For example, this picture shows 3 different citations of the same paper. Given the above challenge, we found that citation field extraction is a useful testbed for sequence labeling problem. It's also an important step in constructing scientific citation graphs such as Coherent and WebKB, and also provide useful information for scientific document classification as well as entity resolution. Due to the nature of the task, it's hard to collect a large-scale human annotated dataset. The only public available dataset has only 2,000 annotated citations, which is not suitable for training and evaluating deep neural networks. Most previous work focused on complex modeling of the input and output sequence. In this work, we hypothesize that straightforward deep neural network can achieve better performance given sufficient amount of training data. Given that collecting human annotated data is costly, we found that to use a noisy auto-generated dataset. Firstly, we propose a simple and reliable data generation process using BibTeX technology. We then show that our dataset can be used to improve the performance on a human annotated dataset. We also introduce a new benchmark for the CFA task on the collected data. A citation string can be generated from a given BibTeX entry coupled with a style using the LaTeX compiler as shown in the diagram. BibTeX allows macro stylings that can change the order of citation fields, adding quotes and extra wording. Some citation fields, such as author name, journal, can be abbreviated and reordered as shown in the picture, thus making it difficult to align citation field with their labels. We propose a simple method to recover citation fields label. A reference string is generated alongside with a citation string by injecting special markers. Alignment between citation fields and their labels are resolved by comparing the string at the distance of label segments. We curate a set of BibTeX entries available on the web and generate label citations for them. The resulting dataset, namely the BibTeX CFE, has roughly 41 million label citations with 59 segments labeled. Citation strings have rather different structures than typical sentences. Thus, pre-trained features on Wikipedia text might not be a good fit here. Since we have sufficient amount of data, we also train a mass language models and use them as a pre-trained features. A standard fine-tuned sequence label models is considered to apply various aspects of modeling. Notice that we don't use CRF either. We compare the models trained with and without our dataset on the UMass CFE dataset with some standard baseline and the state-of-the-art models. On the left are some application studies. By using the pre-trained features, the deep neural network models already achieve decent F1 after fine-tuning with the UMass trainset. Using the feature pre-trained on our data seems to help most the times. Finally, augmenting the BibTeX data and the UMass data gave us the new state-of-the-art on this dataset. We further look at individual labels F1 and include larger scan and loss in table 4, and see only a minor decrease in performance. Having showcased that our BibTeX CFE dataset is useful for human label dataset, we propose a new benchmark on this task as the UMass CFE is fairly small. Overall, our proposed baseline achieved high F1 of 97%. We also provide a domain-specific benchmark for the CFE task. In conclusion, we confirm our hypothesis that better performance can begin by training deep neural networks with large-scale data. We also release the Cohen data to reproduce the experiment. We leave the task for further improving this task to future work. So this concludes the presentations. We welcome you to check out the complete paper at the provided link. Thank you.